Apologies for the title, but I'm more going to be talking about this object here, Bennu, rather than space weathering. There'll be a little bit of space weathering, but mostly spectral bluing in this talk. So here we go. All right, most of the talk's going to be about a paper that I published last year in Icarus on spectral bluing induced by small particles, and how we can understand that using mean Rayleigh scattering. I'm going to talk about 3 takeaways in this talk. That spectral bluing does actually happen not just in atmospheres, but also on surfaces when particles are close packed. Takeaway 2 is we can use this effect to measure the size of particles and to estimate the most likely grain sizes on these bodies when we see this process happening. And takeaway 3 is that the process is probably happening on Bennu and certainly on other solar system objects, as I'll show you with some example spectra. Okay, so first one. So we're all probably familiar with Rayleigh scattering in our atmosphere. It's the blue that we see in the sky. And here is an Earth-shine spectrum showing a really great Rayleigh scattering curve here in the visible, and hence our eyes are sensitive to it. This slide is an extract from the paper that is basically designed to convince you that we have a strong wavelength dependence with Rayleigh scattering when we envisage the operation as taking place as scattering from a spherical dipole, as Rayleigh did when he first derived this. You actually end up with a k to the 4, and k is the inverse wavelength here. And that means that the shorter wavelengths scatter more effectively in the Rayleigh scattering process. So there's no reason why this shouldn't happen for particles, because we can also treat them, if they're small enough, as dipoles. Or at least that's the thinking. All right, so this is a single dipole scattering by itself, and you can see that away from the dipole, we actually get nicely formed circular-looking waves moving away from the dipole. But what happens if you introduce another dipole or another particle in close to it? You get this close packing sort of situation. Does this upset the Rayleigh scattering effect at all? Well, theoretically, we actually don't know how to answer this question yet, but experimentally at least, Roger Clark has done quite a lot of experiments introducing carbon black or nanoparticles about 0.2 microns into water ice to try and replicate things that he's seeing in the Saturnian system. And this is from a paper in 2008 in Icarus, and he also had another paper in 2012 looking at introducing carbon black and getting this this bounce feature or this high peak in the visible that you see here. These are all experimental data. So experimentally, we have good evidence for this spectral bluing taking place in the lab. Second takeaway is we can use this peak, in fact, to estimate the size of particles. And this is all gone into in extensive detail in my paper. And you really need to just take away that we have derived an analytical relationship to give us the most likely grain sizes as a function of weight of size for wavelengths, including optical constants of n and k here, or n and kappa. And we can use this, the Rayleigh scattering assumption, to estimate where the most likely places in the spectrum are for spectral bluing to take place, given that you have a certain particle radius. We can turn this into a plot, skipping over all the map now. We can turn this into a plot for the most likely spot to find spectral bluing occurring. So if you're actually seeing spectral bluing occurring at 1 micron, for example, then you could put bounds on the size of the particles that could possibly affect this Rayleigh scattering, bluing situation. And so you might estimate that you have about 0.3 micron particles causing it if you see it in the 1 micron region. If you see it invisible, which is most likely, then you will be estimating it maybe 0.25 micron sized particles. So this is a lookup table for your use should you see this sort of effect. So this is that's for a single size distribution, which of course is not going to be the case in nature. So when you introduce a size distribution, what happens, and this is related to what I was asking Amanda Cook earlier about whether we see roll-off in some of her observations, if you introduce a size distribution, then you'll get a spectral roll-off. So the bluing won't continue as we saw in the Earthshine spectrum. You'll actually see a roll-off towards the 0.3 to 0.4 micron region, for example, if you have a large enough size distribution. So you can actually use these sort of measurements to constrain the size distribution as well. All right, so takeaway message 3 is that this process may explain spectral bluing that we are now seeing in observations of asteroids. Firstly, this is a figure from my paper just illustrating a couple of different examples of where spectral bluing is taking place, and also estimating a grain size and putting limits on the upper and lower grain sizes that would be required on these surfaces to affect these Rayleigh scattering peaks. So you can see the first two, or the first three actually, are from Saturnian system, Epimetheus, Dione, and the ring system in Iapetus. The moon also, in some locations, is showing a peak, spectral bluing peak. And the reason why I actually got interested in it is that also in Utopia Planitia on Mars, we have the same effect, the spectral bluing effect. And so 0.5 micron grain size particles would be most likely to be causing this effect. Also comet Holmes as well. All right, so just a couple of examples of ground-up meteorites that this was reported in Clark et al. 2011, where she actually looked at comparisons of the spectra of Bennu that she had got. These are dots, and the lines are ground-up particles of various meteorites, and you actually see that she has very strong spectral bluing occurring in the visible out here as well. How could this actually occur? How can we get these fine grain particles? Well, of course, there's going to be many mechanisms for getting these, and this is the crux of why I'm here, is to discuss this with people in the asteroid community, and how might we get these fine grain particles onto the surfaces effectively, and what can we use this method to attack geophysical problems with. And here's at least an inspiring image from epoxy, looking at Comet Hartley 2 and fine grain material being blown off its surface. But now for the crux of this talk. So these spectra here are all taken of Bennu, and the red spectra here is from Beth Clark's work in 2011 that I just showed spectra from. And the green and blue spectra are from Binzel et al. 2015, where he was following up the observations of Clark. Unfortunately, the Binzel spectra do not go shortward of 0.8 microns, which is the critical region for the effect that I'm actually talking to you about today. So, but Binzel did realize that, or did point out that the generally negative slopes of the Clark et al. And also Hergenrother results were not repeated by his spectra. His spectra all showed this strong positive slope. And he looked at the possible differences for this, and he came up with the fact that the observations that he took would have been taken when Bennu was in a latitudinally adjusted geometrical situation, so that he would have been looking at a different part of the body. In fact, he would have been looking at what is now thought to be an equatorial ridge on Bennu. This is data from shape match of Bennu that we have now from Nolan et al. 2013, showing an equatorial ridge here on Bennu, and it's thought to be caused by the Yorp effect. And we also do see equatorial ridges on other NEAs as well. So this could be an important sort of effect to investigate with as many physical methods as we can. And Binzel's results actually suggested to him that there was a finer grained regolith in the equatorial region and coarser grained regolith in the higher latitudes. However, he didn't include the critical visible region, which is, I'm going to advertise to you that we really do need to get this visible region in order to characterize the sub-micron grain size particles. Can we actually do that? Well, yes, fortunately, we do have a chance. On board Osiris-Rex is the OVIRS instrument, and that is going to critically cover the 0.4 to 4.3 micron region. And they're going to get spectral coverage, 20 meter spectral pixels on the surface and global coverage of Bennu. So they should be able to tie down the spectral bluing effects over the entire surface of the body and tell us whether there is a difference between the equatorial and the high latitudinal regions. And then we can start to try and tie down geophysical effects that could account for this. All right, so I just want to put out this final advertisement. If anybody has spectral bluing that they see in their data, particularly in the visible, then please let me know. I'm trying to put together a database of spectral bluing observations, and you can email me at abrown.ceti.org, at ceti.org. Thanks very much. A couple of questions.
Excuse me. I have a Carly Peters, Brown University.
Hi, Carly.
I have a question and then a comment which may lead to a question. My question is, have you considered phase effects, and which way do the phase effects go?
No, I haven't considered phase effects in these.
Can you calculate it so at least you can predict?
Yeah, well, if you're going to look at phase effects, you'll have to introduce assumptions about the shape of the scatterer that you're scattering from. And so, at least in this first paper, I just concentrated on small spherical dipoles and left out the important effect of phase effects.
Well, what you might at least do then is look at the phase of the three observations you've got and see if they're the same or different, and that might give you a clue.
Yes.
Second, the comment I had is that we have some lunar samples where a group at JSC, led by McKay et al., did a extremely careful size separate of a well-developed lunar soil, all the way down to 1 and 2 micron size separates. They were looking at it as a health dust hazard. But we have spectra of those, and as you probably know, lunar spectra are all red. But as you go down towards the 1 and 2 micron separate, they flatten out in the near infrared.
That's nice.
So I'd like to
Absolutely.
maybe talk to you to see if that's consistent or not consistent with what you're doing.
Definitely, yes. I'll talk afterwards.
Okay.
Dan Britt, University of Central Florida. What would happen to your model if you mixed in opaques?
Well, actually, in the paper, we show the effect is relatively insensitive to the optical constant. There is some effect, but
if you've got an absorbing species,
yes,
you're not scattering. You're not just scattering anymore. You're taking some of your photons out depending on the path length.
Yes.
Just a thought.
Right. Yes, that's true. That's true. And basically, I assumed that the optical constants didn't change over the wavelength ranges, so we're just zeroing on the size effect of the scattering. So the Rayleigh.
Yeah, but you've got a mixture of things that are wildly different optical constants, and especially some of those will have a wavelength dependent effect on how they relate to light.
Absolutely. Yeah. Yes, no, it's good, Dan. And then, so that's when we'll end up with spectral bluing superimposed upon absorption band and stuff like that, as you see in the Saturnian system and stuff like that. So it is tricky because we don't know the composition. It could be, we could fool ourselves if we're not careful or not fortunate. This could be an absorption band here rather than a spectral peak. So you're entirely correct.
Yeah, well, not only that, that opaques, especially metals, have kind of odd effects in that wavelength range depending on particle size. Yep. And it's not well characterized by the model. Right.
So 2 slides further, and you're using Fartley 2 as an example.
Four.
There we go. During the flybys of Comet Halley, they did see some very small particles and a steepening of the size distribution into the very small particle regime.
Yes.
But what you're seeing here is fist-size chunks of ice coming up. So it's a good visual, but it's not true.
Okay, thanks, Diane. And that does remind me that I should have mentioned Amanda and Tim's talk from earlier today, where they looked, and I know you were involved in the work too, where they were looking at Rayleigh scattering off into the visible. I've only become aware of that today, but this is definitely a fact that should match up with the model as well.